Okay, so so far what you have studied, just hold on. Yes, so far what we have studied diversion networks, right? And what is the main component of your diversion network? That is your wear or barrage. That is your main component of the diversion network. So let us first focus on the wear part, not on the barrage. Let us just focus on the wear part. So the design of that particular wear has to be based upon some parameters, right? For RC construction, there were some codes upon which, on the basis on which you design that particular structure, right? Similarly, the design of wire, there has to be some parameters, right? Look, this is a wire, and below it there is one impervious floor, right? This is the uh, this is the diagram of a wire. Okay, so what are the things that what do you mean by the design of the wire? So in order to design it, what are the parameters you require? You need this thickness, right? You need to find out what will be the thickness of this part, what will be the length of this part, you need to find out, right? This needs to be found out, this also needs to be found out. And what are the other things? This thickness, if you have any doubt you can ask me. This thickness you need to find out, right? And also this floor length, right? On the basis of these four parameters you can design that particular wire. If you don't have the values you cannot design it, right? So what are the data we have got? Just wait. Okay, so what we need these four data upon which we can design that particular wire. So what we know, we only know what is the head of water here, what is the head of water, we know that. And what is the head of water here, so we can find out the head difference, right? What is the head difference, we can find out that. On the basis of that particular, and also all the soil properties, adjacent soil properties, there are soil here, right? Here there are soils. So on those parameters we have to determine these four values, this thickness, this length, the floor length and the floor thickness. Those four values if you can determine, then we can design the wire accordingly. Okay, so for that purpose there are some theories being adopted by three different scientists known as Bleek, Lenz and Khosla. These are the three scientists. Firstly, today what we will be studying, we will be studying Bleek's theory. Okay, we will be studying that particular theory. So it is known as Bleek's creep theory for seepage flow. Bleek is the name of the scientist. That's why we'll be going by word explanation of this. Bleek's creep theory for seepage flow. So Bleek is the name of the scientist, right? Creep theory. What do you mean by creep theory? Yes. So what do you mean by creep theory? The percolation of water. Here water is being flowing like this within below the your structure, below your floor, impervious floor, and it will emerge out from this point. So this percolation of water, this is known as creep. Okay, so that theory is known as creep theory. That seepage is known as creep. So that theory is known as creep theory. Okay, and for seepage flow. So this theory, that's Bleek's creep theory, is only designed based on your subsurface flow, not on your surface flow. The failures, it is the failure due to the subsurface flow, that is only taken into account, and accordingly it is being negated by your design. Means to cancel out the effect of the failure due to the subsurface flow, that only is taken into account for your design purpose, not the surface flow. What are the surface failures? What were the surface failures? Your what anybody tell me, what are the surface failures? Your hydraulic jump and the score, those two are the surface failures, right? There was hydraulic jump, and what were the two subsurface failures? those were your uplift pressure acting like this, uplift pressure, right? And another was failure due to piping. There was a pipe like thing forming here. So those two were the surface subsurface failures, right? Yes or no? Hello, anybody listening or not?
Yes, sir.
Yes, so those two were the failures due to your subsurface flow, right? That is your uplift pressure and your failure due to piping. So those two parameters were only taken into account by Bleak, and the structure was designed accordingly. Not the else means the surface flow. Those failures are not taken. Okay, under consideration. So what Bleak did, he just took the your subsurface flow, that failures due to subsurface flow, and just found out these two what are the subsurface things here. The what was the structure within your surface, this floor only, this is above your surface, right? This wall type structure is above your surface. So he did not design it for this means this wall he did not design. What he did, he just used his theory in order to design this particular floor. Okay, so what were the parameters he found out? He found out this thickness. This is your what, just hold on, I just, so this is the wire, right? And this is your floor. So he did not design it for this part. What he did, he designed it for the floor. That is, he found out what will be the thickness of this floor and what will be the length of this floor. He found out these two values only. So you can see that the name Bleak's creep theory for seepage flow. You can understand that. Okay, and those two were only find out. You can were only found out. So we can see it in this class that how those two parameters have been found out. Okay, so there were few assumptions that was done by Bleak. There was been adapted. Those were being adopted by Bleak. What were those assumptions? Bleak developed this theory for surface flow only. Yes or no? I already told that the Bleak, what he did this theory based on subsurface flow only. He did not take into consideration the failures due to surface flow. Okay, so he developed this theory for subsurface flow. This is one assumption. Okay, and also as well as it is also a limitations also, because there are going to be failures due to your surface flow also, but he did not take it into his books. Okay, so this is one assumption. Second assumption is that Bleak assumed that the percolating water follows the outline of the base of the structure, which is in contact with the subsoil. Okay, so what do you mean by that? He assumed that the water will be flowing in contact with this floor only. There will be the flow of water will be like this only. There won't be flow like this, or this type of flows won't be there. The flow of water, the percolation of water will happen with with respect to the base of your structure itself. Okay, everybody have understood this point. There won't be any flow like this. Like there will be flow naturally. There is a flow like this. Elliptical flow like this occurs. Okay, but what he did not take into he did not take that into his assumption. Okay, what he did, he just made sure, he just took that assumption that the seepage of water follows the base of the structure only. Okay, that is his assumption. Second, the length of path traversed by percolating water is called the creep length or length of creep. So the look, this is your wire. So what will be the length of the creep? He took this value as the floor value and he denoted it by L. Okay, this is another assumption. As he took as he noted down that there will be flow of water along this track only, there won't be any flow like this happening. there won't be any percolation of water happening like this. So what he did, the water traveled, the distance traveled by the percolating water is the length of this flow, right, and that is known as your creep length. Okay. Bleak further assumed that the head loss per unit length of creep, the head loss, there is head of water here, there is a head of water on the downstream as well. So there will be a head loss, this is your head loss, right. This head loss per unit length, it is denoted by, head loss is denoted by HL. So that head loss per unit length. So what is the head loss per unit length? HL divided by L. So he assumed that this value will be constant throughout, and that line, there is a hydraulic gradient line, so it will be looking like this. Okay, as this is constant, so there it will be a straight line, your hydraulic gradient line will be a straight line. Okay, so this hydraulic gradient line will be a straight line as the slope is constant. HL by L, that is assumed by Brick as constant, and it is denoted by I. Okay, so the I that is constant, HL by L is constant, so it will take up the shape, this curve will be taking up the shape of a straight line, and that is another assumption. Have everybody understood this point? Yes or no? The slope here would be the same, that is I. The slope here also will be the same, that is I. Along your hydraulic gradient line, this particular line is known as hydraulic HGL. Okay, that is known as hydraulic gradient line. Yes or no? Everybody have understood? Tell me the assumptions. Any doubt? I mentioned 4 assumptions. If you have any doubt on that, tell me. Anybody? Yes or no? If you have any doubt, if you have any problem regarding understanding, you can tell me. বাকিরা কি ক্লাস করছে না? The others are not doing, are not in front of your phone or what?
Hello, sir.
Yes.
Sir, can you explain about creep once again?
Yes, creep. The length, look, the length traveled by the percolating water, he denoted what Bleak did. The length traveled by your percolating water, he denoted that length by L, and that is known as creep length. Okay, he assumed that the water will flow following this flow, right. It will be flowing in contact with this floor, so the length of the floor will be itself the length of the if your thickness, this thickness is very less, suppose this thickness is very less, the thickness T is way less than your L value, then what is the total length traveled? L plus by the percolating water, what is the total length traveled? L plus 2T, right. L is the length of the your flow length, right, and T is the thickness. So water will be from this point will be coming down, then it will be going like this, and then it will be going up like this. So the total length, what is the total length traveled by percolating water? It is L plus 2T, and if T value is very less, then we can neglect this part, and what will be the value of creep length? The value of creep length will be itself L. Okay.
Okay, sir.
Yes. Rest clear? Everybody clear? These are the assumptions. Okay, so let us go to the next part. So look, let us concentrate on this figure. Okay, we in order to gain stability of the structure, in order to provide it for, means in order to provide strain to the structure against your uplift failure, what we did, I think everybody know that what we did, we inserted a sheet pile or a cut-off pile at the upstream of the wire, right? Yes or no, everybody? We provided a cut-off pile at the upstream side in order to provide resistance to the uplift pressure. We did that. Similarly, in order to provide resistance to the piping failure, what we did, we inserted another cut-off pile at the downstream side. Yes. Can everybody remember that? We did that, na? In order to provide resistance to the failure due to subsurface flow, we provided one sheet pile at the upstream as well as one at the downstream side. Okay. Similarly, what we did, we provided another. If you can see the figures of the vertical drop wires, your rock fill wires, and another one was concrete wire, right? On in those three figures, as per the note I have given you, you can see that there were three piles being used, right? Three piles were at, one was at the upstream, one was at the downstream, this is at the upstream, this is at the downstream, and another one was at the intermediate position, right at the construction of your wall face. There was another pile being inserted. Why those were inserted? In order to increase the creep length, the water has to flow in this way, right? It can, the piles are impervious layers, water cannot go through within the piles, right? So if there is one impervious layer like this in the form of sheet pile, what will happen? Water from the hair will have to get down and then get up and flow in this pattern, like it has been displayed in the figure, right? Everybody just responds yes or no. If there is one impervious layer, then water has to follow this track, it cannot go directly like this. If the like in this figure you have seen that if the floor, if there were no sheet piles, then what will be the nature of the flow? It will be flowing like this in contact with your floor. But what will happen if we insert a pile here? It will act as a obstruction to your flow of water. So water has to flow like this, and has to come up and then flow in contact with your base of your wire, right? So concentrate on this figure, okay? So there were three piles being inserted. The length of those piles each are denoted by D1. The intermediate pile is denoted by D2, the length of the pile, and the third length, it is denoted by D3. Okay. So initially the water head was at this point. Just wait. Okay. So initially, what was the water head? This is your water level, right? So initially the water head was here. Okay. So what will happen? The water has to traverse this point, this height, this length, right? It has to go down here and then go up. So similarly, water has to come down from here and then go up. Similarly, these things will happen in all the three piles, right? So what is the, firstly, what is the total creep length? Look, the total creep length, that is denoted by L, it is equal to, you can understand that, D1 plus D1, another D1 is there, right? D1 plus D1 plus this length is L1 plus D1 plus D2 plus this length is L2. That means D1 plus D1 plus this one is L1 plus this one is D2, another D2, then this is following this line, that is L1, then again D3 and another D3. So this is the total creep length. Have everybody understood this part? This is the total creep length. So it can be replaced by your L1 plus L2, that is denoted here by B. So it can be replaced as B, and the 2 times, there are 2 times of D1, D2 and D3. So whole, if you take out 2 as the common factor, then 2 times of D1 plus D2 plus D3. This total plus B that gives us the total creep length. Yes or no? If there were no sheet piles, then water would have directly traveled from here to there. Then what will be the total creep length at that point? That creep length, if there were no sheet piles, then your L value would be equal to B, because there were no D1, D2, D3. That time it would be equal to B, but as you have inserted 3 piles, your total creep length will be equal to B plus 2 times that of D1 plus D2 plus D3. Everybody understood this one? Just tell me.
Yes, sir.
Yes. So the total creep length is this one. Okay. So what will be the head loss per unit length, or that is known as hydraulic gradient, denoted by I previously mentioned, right? The hydraulic gradient denoted by I, that is head loss per unit length. That is your head loss, it is denoted by HL. Okay, so per unit length, that is the total creep length. What is the total creep length? It is, we will replace L by this value, right? This is your total head loss per unit length. Okay, Bleak assume that value na, that HL by L will be constant throughout your flow. It will be the HL, the head loss per unit length. That per unit length means the creep length. That will be constant. So here the creep length is B plus D, 2 times that of D1 plus D2 plus D3. So the head loss per unit length will be HL by this L value. Okay. So what will be your hydraulic gradient line? What will be it? It will be looking like, it will be looking like this, because initially you can see that the water level was here, right? The the gradient line was here. So there the net HL by L is the uh, rate of change, rate of head loss per unit length, right? So what will be the what means what will be the deduction of your this abscissa, this ordinate? What will be the deduction of this ordinate? It will be into 2 times that of D1, 2 times that of D1. Okay, this will be the, because water has to travel, sorry, just wait. So water has to travel this length, 2 times that of D1 it has to travel. So there will be a head loss of HL into 2 times that of D1. This will be the head loss here. Then it will follow this straight line. Okay. Then here also there is another sheet pile there. So there will be another loss of head, that is equal to, this value will be equal to HL by L into 2 times of D2, right? Then there will be like this, and here there will be another loss. This is equal to HL by L into 2 times that of D3. Have everyone understood? Look, this is the diagram it will take up. Their hydraulic gradient line will be like this because of the sheet piles. Because naturally it is a straight line, okay, but here because there are sheet piles, so what will happen? It will be direct loss of head at this point as well as at this point as well as at this point. There will be a direct loss of head, because water has to travel through those 2 times those distances, 2 times that of length of those sheet piles, right? So the hydraulic gradient line will be looking like this. There it will be like this. Then there will be a downward direction, a vertical line will be like this. Then it will come down like this, another vertical line. Then it will come down like this, another vertical line. It will end here. Your hydraulic gradient line will be looking like this. This is your hydraulic gradient line. Okay, have everybody understood this? Tell me. Bit complicated this one. Hello.
Yes, sir.
কিরে রিয়াঙ্কা বুঝতে পেরেছিস নাহলে বল এভরিবডি
হ্যাঁ স্যার বুঝতে পেরেছি।
anybody having any doubt you can tell me. As per Bleak, your hydraulic gradient line, if there were no sheet piles, then it should have looked like this is your wire. It should have looked like, and this is your floor, right? The hydraulic gradient line would have been looking like this. But as because there are sheet piles, so there will be a loss of head here, and that is equal to your HL by L into 2 times that is uniform, right? HL by L is uniform throughout, and as because there is a 2 times that of d1 distance being traveled by your that of your percolating water, so the head loss here will be HL by L into 2 times that of d1. Similarly, from that on the slope will be constant, then there will be another slope, vertical slope like this, then it will come down like this, and at the end this will be the ultimate slope, that is HL by L into 2 times that of D3. Okay. At each juncture of your sheet piles there will be a head loss. Okay. So what will happen if this particular head, that is HL by L into 2 times that of D3, if this is greater than 0, what will happen? If this head is greater than 0, then what will happen? Water will start to percolate from this point. Yes or no? This will water will start to percolate from this point. If it's equal to 0, then there will be no percolation of water. But if it's greater than 0, there is a difference of head, right? So water will start to percolate from this point. Okay. So in order to avoid that, what we do? We can increase the value of L. The L is increased. L is increased. So there are two ways how we can increase L. What we can do? We can increase the length of the floor. Yes, we can increase the length of the floor, right? That is one way you can increase the value of creep length. And also we can do another thing, that is we can increase the length of the sheet piles. We can increase this length. Okay. So these two ways we can increase, means if we increase d1, d2 and d3, if we increase those values, then automatically your L will be increased. L is L equal to what? B plus 2 times that of d1 plus d2 plus d3. We can directly increase that B value, that is B, this is the B value, right? The spacing between the length of the floor, that is your B value. So we can increase that B value, or what we can do, we can increase all the 3 D values, or any one or any two of the D values, you can do that also. Okay. So next comes your safety against next comes your safety against piping or undermining, that is the piping failure. Okay. So for this, what Bleak got, he got the value of the thickness. I already mentioned, he just found out these two values, that is the thickness and the length. Okay, that is the B value, the thickness T and the B value. He just found out those two values for the design purpose of wire. Okay. So from this, due to the safety against piping, he found out the value of the length, that is the B value. He found out that what will be the length of the floor, he found out that value. So for that, what he did, he developed another constant, another coefficient, that is known as Bleak's coefficient for the soil. He developed that constant, and that is denoted by capital C, which is equal to the reciprocal of your hydraulic gradient. What was the hydraulic gradient? That is HL by L, that was the hydraulic gradient, right? So what is the reciprocal of HL by L? It is L by HL, right? So he named that L by HL as capital C, which is known as Bleak's coefficient for the soil. So if we just cross multiply it, you will be getting L equal to C times HL. Okay, we already know the value of HL, we already know the value of total head loss. That is already known to us from the particular dam or particular river work what we have constructed. We already know that particular value of HL. Okay, so this constant that is dependent on the soil properties. This has been calculated from soil testing. Okay, and you can see that for various types of soils the value of C ranges from 5 to 15. So the value of C on that particular, for a particular type of soil, it will be constant. So HL is known to us, we can find out C from the soil properties. So what we can do, we can provide, we will be able to know the value of total length. Okay, the total creep length, we will be able to determine that from this particular formula. C into HL will be able to know the total value of the creep length. So we can provide that particular floor length accordingly. Have everybody understood? So in this way your length of the floor was determined.
Yes, sir.
Yes. So next is your safety against uplift pressure. So look what big from the safety against piping, what was being developed, this B value I have got, right. So another value we need to know, that is T, the thickness. How can we know that? Look, what is the uplift pressure? P equal to that uplift pressure, P that acts to upwards, right, that will be equal to, suppose we take, just let me change the page. Okay, this is your wire. Okay, let the hydraulic gradient line be uniform like this. Okay, so for our calculation purpose we are taking it like this. So let there be any point on the hydraulic line, suppose there is a point P. Okay, so let that head of water be denoted by H. Here the head is denoted by H. Okay, and the thickness here, let us assume it to be small t. Okay, and the total length from the base of your floor up the height of the point, the height of the point P, let it be denoted by H dash. If you have any problem, just tell me. Okay, let it be denoted by H dash. So H dash equal to your H plus T. I think everybody is clear with that. H dash equal to H plus T, right?
Yes, sir.
Just wait. So H dash equal to H plus T. Okay, so what will be the pressure acting due to this uplift at the point P? Suppose at the point P we are considering that only. Okay, what will be the pressure acting? P upwards, let us denote it by this, it will be equal to rho gh. Everybody have studied that, I think, in your buoyancy force. Everybody know that rho gh, right? That is the upward pressure. Yes or no? Everybody have studied this one, right?
Yes, sir.
Upward pressure
Uplift.
equal to rho gh. Yes.
Mhm.
So here there is only water, so this rho will be equal to rho w, and this value rho w into g, this will be equal to your unit weight of water. That can be in soil mechanics you have studied that can be denoted by gamma w. Okay, so pressure acting upwards will be denoted by rho w into h. Sorry, this one will be h dash. Yes or no? This is the pressure acting upwards. So there is a floor, this is the thickness, okay. So what will be the pressure acting downwards due to this self weight of the floor, that will be equal to similarly rho c, that is the concrete, okay, into g into t, this will be t, the thickness is t, right. So this will be equal to t. So this part similarly it is equal to rho c into t, that is concrete. Rho c you have denoted it for the concrete part, okay, that is equal to t, okay. So what is the value of rho c? We can replace it by g times into rho w into t, that is the force acting downwards, okay. We can denote it like this, where what is the value of g? It is the specific gravity, right. Specific gravity of a particular material, what is the value of specific gravity of a particular material? The unit weight of that particular material divided by the unit of water, right. I think everybody know that, yes or no? Yes or no?
Yes. Yes,
So,
sir.
so if we equate those two, in order to let this be stable, these two pressures will be equal. This will be equal to this, right? These two will be equal to, means this pressure acting upwards due to the uplift will be equal to the pressure acting downwards due to the self weight of the floor. Okay. So let us see here. So that is the uplift pressure is gamma w into h dash. So if we equate those two for equilibrium, what we can find out? We can find out that, look, this will just cancel out, this rho w and rho w will cancel out, right? These two will cancel out. So what we are left with, h dash equal to g times into t. We are left out with this. Okay. So you can see here h dash equal to g times into t. Okay. So if we subtract a t from both sides, what we will be getting? H dash minus t equal to gt minus t, right? What is the value of h dash minus t? That is your h, yes or no? Just look here, h dash minus t, this has already been, I have shown you, right? H dash minus t equal to h. So h equal to, if we just bring it on the both sides and then cross multiply, what will be getting? T value will be equal to h by g minus 1. What is the value of g minus 1? It is the submerged specific gravity of the floor material. Okay. In soil mechanics, I think you have studied that g minus 1 is the submerged specific gravity of the floor material. So this h value will be changing. Look, this g minus 1 is constant for a particular floor material, your specific gravity won't be changing, right? So the denominator, that is g minus 1, will be constant. What will change is the value of h, that will change. Look, h here is something different, right? And if we move here, the h value is going to be less. There is a decrease, there is slope. So there is a decrease in the slope, means there is a decrease in the value of h. The value of h here will be maximum, it will, here it will be minimum, right? So what we can do, there are two ways we can construct the value, means we can provide the value of t. But generally what is being done, we provide a uniform thickness considering the head here, the head at the extreme point, the maximum head, that is denoted by capital H. We construct it accordingly, taking the head, that h value as capital H, which is the maximum head. We take that particular h value, okay, for your determination of the value of t. We do that, we can do that, okay. So accordingly it will have a uniform thickness, the t value will be uniform throughout. Another thing we can do, as the value of t is changing, means there is a decrease, a linear decrease in the value of h. This h is decreasing, right? Here it is maximum, then slowly is going down and it is attaining its minimum value. There is a linear decrease in your value of small h. Yes. So what we can do, we can take it as a function of h and design it accordingly. So what will be the thickness of your floor? It won't be looking uniform, it will be looking like, here it will have maximum width, then there will be a linear decrease in the slope in the thickness, and it will be looking like this. We can construct it in both ways. Have everybody understood? Just tell me this point. What we can do, there are two ways. One, we can take out the maximum h value and accordingly we can provide the thickness, then the thickness of the floor will be uniform. Here what will be the thickness here will be exactly the thickness here also, there won't be any change in the value of t. But what if we provide a sloping floor, means if it is a function, if we provide it as h is changing, if we provide the floor accordingly as a changing value, then what we can do, we can provide a non-uniform thickened floor. We can do that. Have everybody understood? Just tell me. This is the way of construction of the floor. The thickness and the length has been determined by your two factors, that is direct uplift and your piping failure. Just tell me whether have you understood or not.
Yes, sir. Understood.
Yes. So what are the limitations of Blink's creep theory? This theory has no distinction between horizontal and vertical creep. Look, we considered, what happened? Yes. So what Blink did, he did not distinguish between the horizontal and vertical creep. So what do you mean by horizontal and vertical creep? There were sheet piles, right? This creep is known as vertical creep, and after that there is flow of water like this, a horizontal flow of water like this. This is known as horizontal creep. Okay, creep. So he did not distinguish between this vertical creep and horizontal creep. He just used a uniform value. That's why you have multiplied it by 2 times that of d1. That value you have multiplied. But it is not the case. There is a distinction between the flow of water, horizontal and vertical is not same. So everybody know that the flow of water from the vertical flow of water is more than that of horizontal flow of water, right? I think everybody know that. So that creep value means the creep, what he did not distinguish between the horizontal and vertical creep, that should be there. That is one limitations. Okay. Next is, he did not explain the idea of exit gradient. The water coming out from this point, he did not give any idea on this. There was no idea being established here. Okay, this is known as the flow of water from this will be known as exit gradient. He did not give any idea on it. Okay. Next is, no distinction between outer and inner faces of sheet piles or the intermediate sheet piles, whereas from investigation it is clear that outer faces of the end sheet piles are much more effective than the inner ones. He took the same value for creep, he took this as d1 and also for this one as d1 also, but here the outer surface is much more effective. It will provide more resistance to the flow than your inner surface. Okay. So he did not distinguish that between the inner surface and the outer surface. The outer surface provides more friction than your inner surface. Okay, that is another limitations. A loss of height does not take place in the same proportion as the creep length. There is not the means what he assumed, his most important assumption was that the loss of height is constant throughout its length, right? So that thing is not proportional. It is not proportional actually. It follows the sine curve. We will be seeing it in Khoslas theory that it follows the nature of a sine curve. That flow of water, it means the hydraulic gradient line. It follows the sine curve. It is not a straight line. Okay. But this is the limitations. Any question? Anybody having any question on this?
No, sir.
You can ask me. I'm giving you 1-2 minutes time if you can, if you have any doubt, because the Blick's theory part is being completed. Okay, next day we might do a problem, 1 or 2 problem, but this thing has been completed. The theory part has been completed for Blick's theory. Anybody having any doubt can raise it, or even from your previous classes. So I think none of you have any doubt, right? So now we may leave.